when we're talking about reactivity of specific functional groups, there are always things we want to consider. One of them, of course, is acidity. So we're going to review a little bit about ranking our acidity. Now here we all have alcohols, so we're looking at our stability of our resulting negative charge on an oxygen. So we're looking at the differences there. So as far as our physical properties of our alcohols, the OH of an alcohol can have a big effect on the physical properties. We see a huge difference in boiling point when we have an alcohol there because of the ability of our alcohol to hydrogen bond with another molecule of itself. So that increases our boiling point significantly, where if we look at ethanol, the boiling point is around 78 degrees Celsius. Our differences, of course, is hydrogen bonding. Because of the hydrogens in our hydroxyl groups, we can attract water molecules strongly. So, depending on the R group size, alcohols may or may not be water soluble due to their ability to hydrogen bond with water. So, of course, the question is how big the R group is. Remember, the carbon containing part of the group is going to be hydrophobic, whereas the alcohol is going to be hydrophilic. And the alcohol end is relatively small. So if the hydrophobic end is relatively small, we can get water solubility. We see methanol is soluble in water. We only form one solution. We see ethanol mixes with water. It's miscible. Of course, if you look at something like your alcohol that you drink, clearly there's water in there, and it doesn't form two layers. So we know it's miscible. But as our hydrophobic region gets bigger, and our branching blocks our alcohol group and its ability to hydrogen bond with water, we get less water solubility. So larger carbon chains don't readily mix with water, and we don't have water solubility for bigger. Now, the more alcohols we have, the more water solubility we impart on the molecule. But of course, if we're just talking about one alcohol, what we usually see is around 3 or 4 carbons is going to be miscible, but anything more than that, we start seeing immiscibility per alcohol, of course, and depending on where alcohol is on the carbon chain. But we can get more water solubility with more alcohols. Now, in lab, we talk about making things like this more water soluble by reacting it with an acid and forming the anion. The anion would be more water soluble because that's a stronger bond with water than just the hydrogen bonding. Because an anion dipole bond is pretty, well, it's not really a bond, but anion dipole interaction is pretty strong. But what we typically see in a neutral alcohol is smaller R groups are water soluble, but as we get bigger, it gets less water soluble. And that makes sense because, again, the R groups are hydrophobic. Alcohols and phenols are also often antibacterial. As you know, we use isopropanol a lot in the hospital setting as our rubbing alcohol. So the potency as an antibacterial agent for an alcohol depends on the size of the hydrophobic region, as well as the fact that we have an alcohol present. So what we see is that there's kind of a sweet spot in the size of the alkyl chain for real big potency. And what happens is we need our alcohol to have enough water solubility, or it won't come in contact with the bacteria, because the bacteria is usually in a more hydrophilic environment. But we need some hydrophobic region because the hydrophobic region is going to interact with the cell membrane. And that's what's going to break up the bacteria cell wall and kill it. So it needs to be able to interact with the lipid membrane. Lipids mean fat that has big hydrophobic chains. So we need hydrophobic regions to work with that. So an example of antimicrobial agents in the medicine is this guy. What we have is 2 alcohols, so we have water solubility, but we have this hydrophobic region that's able to interact with the cell wall. So this is used for things like eczema and psoriasis. Another example, a stronger antibacterial agent is this antifungal agent, and notice here the difference is we have this long carbon chain that allows it to interact with the cell membrane more of the bacteria because it has this chain. It kind of allows it to anchor in there. And there's been some work for antimicrobial agents with things like polymers that are have big nonpolar ends of the polymer and big polar parts of the polymer. Remember, polymers are really big molecules. And they have been used also to find better antimicrobial agents and antibacterial agents using those concepts. So alcohols are a big part of that, but of course the size of the hydrophobic region is important. So we do use alcohols a lot in synthesis because that, as a final product, they're really useful. So acidity is also affected by the fact that we have an alcohol. Remember, when we are evaluating acidity, we can look at the stability of the conjugate base. The more stable the conjugate base, the more likely our group is able to give up a proton. So when we're looking at alcohols, what we see is we have our atom on a pretty electronegative atom, not very electronegative, but pretty electronegative, oxygen. So that's stabilized, and most alcohols have an acidity of around 16. But that can change based on other things going on with the alcohol. The conjugate base of an alcohol is called an alkoxide. If that R group is, let's say, a ethyl, that's an ethoxide. If it's a methyl, it's a methoxide. Know that terminology? We use it. Now, we've used these before. We've used alkoxides in things like elimination reactions. We've discussed them. You got to realize, though, alkoxides are pretty strong bases. Relative stability, this is fairly stable compared to, let's say, a negative charge on a carbon. But as far as actually talking about a strong acid, most of them are, I think, really low. See, HCl is like negative something. I don't remember what it is exactly. That completely dissociate. So a negative pKa, a really low pKa. 16 is pretty high. Our organic acids are not acidic, but they can be more acidic than other things. So it's not easy necessarily to deprotonate this. We need a base that's strong enough to do so. Not all bases, like for instance, we know our double bond is a weak base. It's not a strong enough base to deprotonate an alcohol. This is not stable enough. So we need a strong enough base to deprotonate our alcohol. So a common way to deprotonate an alcohol, a very useful way to get a very clean ethoxide, or alkoxide, in this case it's ethyl, sodium hydride. Now a couple of things about sodium hydride. What's the first thing you notice about sodium hydride? What's different than any other reagent we've really talked about? What partial charge does hydrogen typically have? Positive. Why? Why? Our hydrogen is typically the more electropositive thing. Let's look at sodium hydride. What's more electronegative, sodium or hydrogen? More electronegative? Hydrogen's more electronegative than sodium. Remember, hydrogen's electronegativity is closer to that of carbon. That's why we say it's nonpolar than a metal. Metals are always going to be more electronegative than our hydrogen, than our carbon, than our nonmetals. I'm sorry, electropositive. So typically, in organic chemistry, we're looking at covalent bonds between our nonmetals. And when we're talking about our nonmetals, carbon and hydrogen are typically the least electronegative. But sodium hydride is an ionic bond between a metal and a nonmetal, and in this case, our nonmetal is hydrogen. So instead of a proton, this is a hydride. It's a hydrogen with a negative charge. Do you think this is stable? No. Hydrogen is small, and it's not very electronegative. So sodium hydride is very, very reactive. Another example of one of those compounds, if I were to expose it to air, it would catch on fire. That's how reactive it is. A hydride, typically we never have the base of the arrow coming from a hydrogen. And that's because we're talking about a proton, a partial positive hydrogen that has no electrons. Here, hydrogen is bound to a metal. That means the hydrogen is more electronegative. That means it has the electrons. That's a hydride. A hydride is negatively charged hydrogen. You don't have to memorize reagents, but you need to be able to look at a reagent and determine, is this an ionic or is this a covalent bond? Where's my partial positive? Where's my partial negative? Which atom's more electronegative? In this case, hydrogen is more electronegative. So compared to sodium, hydrogen's going to accept the negative charge. And remember, sodium metal is very reactive. It doesn't want that electron, so it'll force things to have a negative charge that won't typically have a negative charge. Because it's really, really reactive. It really doesn't want that electron. But sodium hydride has to be stored in mineral oil, and once you dissolve the mineral oil away from the sodium hydride, usually by using hexane or some other nonpolar solvent, then you have to react it very quickly and make sure it stays away from water. Otherwise, it's going to spontaneously react in a very quick kinetic and very exothermic reaction with water in the atmosphere and catch on fire. So sodium hydride is very reactive. What that means is hydrogen, when it's a hydride, is going to act as a very, 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 very strong base. And we can deprotonate a lot of things with a base that's this strong. So if we look at our forward reaction, a hydrogen with a negative charge in our starting material compared with an oxygen with a negative charge in our product, clearly our equilibrium is going to be to our product side. Oxygen is much more electronegative than hydrogen. Also, the other thing about this reaction that makes it very useful is we form H2. H2 is not very reactive. We have to use catalysis to make it reactive. So once H2 forms, the ability for it to go in the backwards reaction is very low. Plus, once H2 forms, it's a gas, and it can bubble away. So remember Le Chatelier's principle that if we remove a product, it's going to push the reaction more towards the product side. So this is a very useful reaction. We can get 100% yield with this kind of reaction because the process of H2 gas being forming and the fact that hydride is so reactive will really drive the reaction forward, and we can get ethoxide very easily. We won't get as strong of a product if we just use something like sodium hydroxide, because the difference between our OH negative and our R group oxygen negative isn't that different. So we're going to be a big equilibrium. So here we're forcing that equilibrium forward. Again, you should be able to look at a molecule like sodium hydride and look at what hydride is equal to. We have an H negative. Here our hydrogen can act as a nucleophile or a base, depending on what it's in the presence of. And it's small, so it can interact as a nucleophile very easily. These are the things you should be thinking about when you're looking at reagents. And again, the thing is, hydrogen is more electronegative than sodium. Sodium's a metal. Alternatively, another useful reaction is actually using sodium, potassium, or lithium metal. They're all in group 1. They all react very similarly. Here, though, this is more of an ionic, a radical reaction because my sodium is giving up its electron. And eventually we're going to form an H2 molecule. But it takes 2 alcohol molecules and 2 sodium metals to form 1 H2. Again, this reaction is forward driven because sodium metal is very reactive and because we form H2, which can't really react in the backwards reaction in and will turn into a gas and go out of the reaction. So both of those reactions can give very high yields of our alkoxide. So in this reaction, sodium gives up its electron, forming a hydrogen radical. Again, not very stable, but sodium can force things to happen. That forms 1 alkoxide. Remember, sodium is not forming an ionic bond between oxygen, it's forming a covalent bond because it's a metal. And then this happens twice, so 2 H radicals can come together to form H2 because H radicals are not very stable. This is a very rapid kinetic reaction as well, because sodium really wants to give up its electron. So once we form alkoxides, we have to consider acidity. So recall from chapter 3, what we can use to get a good idea of acidity is areophluxing. Now, if we're talking about oxygens, they're all in the same atom. So then we're going to go further. Looking at oxygen compared to something like nitrogen compared to a carbon, carbon does not stabilize a negative charge very well. We see very high pKa's. Assuming we're talking about an sp3 carbon, we know a triple bonded carbon can be a little bit more acidic, though still not as acidic as an alcohol. A pKa of an amine is still very high. Our amines much rather accept a hydrogen and form a positive charge than give up a hydrogen. They much rather act as bases. Our alcohols are between 15 and 18, and then of course our halogens, most of them, not HF, but most of our halogens are strong acids because our halogens are good leaving groups. So we know our atom makes a difference. Alcohols are more acidic than amines or alkanes, but they are not, compared to our strong acids, very acidic. They're still fairly weak. They're all weak acids unless we're talking about the 6 strong acids that you learned in general chemistry. Now, compare our alcohol cyclohexanol to our alcohol phenol, and we see that phenol is even more acidic. What's the difference there? Well, in both cases we have a negative charge on the oxygen, but phenol is 100 million times more acidic than cyclohexanol, even though they have relatively the same amount of London forces, because they have the same amount of carbons. The difference here is resonance. We have multiple resonance contributors of phenol, which stabilize the negative charge even more. So that pushes that equilibrium further when we're talking about reacting it with water. Now, in all of our resonance structures, besides our most stable resonance structure, which our most stable resonance structure is our phenol, where the benzene ring is intact, these are still contributing and still help to stabilize, but our pKa isn't as low as you might assume because of the amount of resonance structures, because these resonance structures are not equal. Here we have a negative charge of carbon in these resonance structures, which is not as stable because oxygen is more electronegative than carbon. And also in these resonance structures, the benzene ring is broken, so we lose aromaticity. However, it's still contributing to our overall acidity. Resonance will stabilize our negative charge or our positive charge, but here we're talking about negative charge. So resonance stability is very useful, huge difference. Now what we see here is our pKa of water. Cyclohexanol is not quite as low as water. And that has to do with the fact that when we measure pKa, we're measuring it in water. And cyclohexanol has more sterics around the alcohol that blocks water from stabilizing the negative charge. That's our solvent effects. So that's why we see a difference between H2O and cyclohexanol. The more R groups we have surrounding our negative charge, that blocks water molecules from the solvent from aligning with the negative charge and stabilizing it through solvent effects. So we'll sometimes see that, especially when we don't have any other big difference. But resonance is usually our strongest effect. We also have inductive effects. Inductive effects are typically as strong as resonance effects, but again, that's relative. Depends on how many electronegative atoms you have and how close they are to the resulting charge. But if we compare ethanol and this trichloroethanol, we see the pKa is very different because our chlorines are electronegative and through induction is stabilizing the negative charge of the oxygen. This is not the same as resonance. The electrons are only ever localized to the oxygen, but the chlorine is pulling the electron density towards it, therefore stabilizing the negative charge. Also, that makes the lone pairs of the alkoxide less likely to act as a base to go into Bapford's reaction. So we have electron withdrawing groups. The closer the electron withdrawing groups are to the negative charge, the more it stabilizes, and the more electron withdrawing groups, the more it stabilizes. This is all from chapter 3. Orbital can also have an effect, but when we're comparing alcohols and other alcohols, we're pretty much comparing a negative charge on an sp3 orbital, unless the electrons are in resonance, and then that's of course an sp2 orbital. The sp2 orbital is going to stabilize the negative charge a little bit more, but most of the effects you're getting is coming from the resonance spreading out of the lone pairs. And solvation is the last one. I was just talking about that between water and cyclohexanol. Let's look at that here. We can compare ethanol and terbutanol, and notice they don't have the same pKa. They look fairly close, but remember, each pKa unit is an order of magnitude. So this is a pretty big difference if we're comparing. So why is terbutanol less acidic than compared to ethanol? There's no difference in atom, there's no difference in resonance. There's really no difference in induction. There's no electronegative atoms on these compounds to stabilize the negative charge on oxygen. And there's no difference in orbital. They're both in an sp3 orbital. The difference is sterics and solvents effects. So, because our acidity is measured in solvent, the solvent, if it's a polar solvent, will have a positive in and a negative in, which means it can align near the negative charge and help stabilize. We use solvent effects all the time in organic chemistry to make reactions go faster, to stabilize transition states, to lower kinetics. So we use solvents like that, and this is one of those cases. The less sterics surrounding our alcohol, that means that we can have more solvent molecules stabilizing our negative charge. This effect is usually most prevalent when we don't have any of those other effects to compare to, because the other effects are typically going to be stronger, but they can make a difference, so it's important to remember them. So looking at these examples, if we're ranking these molecules in order of increasing pKa, remember increasing pKa is going to be most acidic to least acidic. First thing, all of our acidic protons and all of these examples are on oxygen, so our arrow is always going to be oxygen. So atom is oxygen, we don't have any difference. We have to look further than that, they're all going to be on the oxygen. So looking at B, what we see is if we deprotonate our oxygen in B, we don't have any resonance effects. We have an sp3 carbon between that pi bond. So we don't have overlapping p orbitals. Our negative charge is being stabilized by induction, though our oxygen is 2 atoms away. If we look at this example, what we see when our base comes in and deprotonates, that's what the B means, just our base. We do have resonance, and in fact, this is a very stable resonance structure that results when we form the negative charge, because our nitrogen has a positive charge in the first compound. So when we form that alkoxide, the resonance structure is going to have a neutral resonance structure that can result. So this resonance structure is a lot more stable and contributing than this one. But this resonance structure where the positive charge on nitrogen is no longer there can't happen unless it be deprotonated. So what we see is a very stable resonance structure. If we look at this example, we don't have any inductive effects, no orbital effects, because we're still in an sp3 orbital, and we don't have too much, so there's nothing attached to the ring. If we compare this one, that's also the case, but we don't expect these two to have the same acidity, because of course this one has more sterics, so it's going to be stabilized the least by solvent effects. So when we're putting this together from most acidic to least, resonance is going to most stabilize our negative charge. The only one that has resonance is that second example, so that's going to be our most acidic. Our second most acidic is the one being stabilized by induction. And then this one that is being stabilized by our solvent because we don't have sterics blocking the alcohol position. And lastly, this one, which again, there's no inductive effects, there's no resonance effects, but sterics is going to prevent solvent from stabilizing. Again, this is just a review from chapter 3. None of this is new. If you're feeling lost, you need to go back and read chapter 3, which I've been telling you since the first day of this class, because we're always going to be talking about acidity. Acidity is very important to this class because we use acid and base catalysis all the time. Oh, well, re-answer it since I started. So, our answer, our strongest to our weakest acid here, of course, B has resonance effects, so that's going to be our most acidic. D has inductive effects. Then A, we're going to have more solvent effects. C is more blocking solvent effects. We don't have any other effects, so C is going to be our least acidic. This should be an easy question for you to answer because we've talked about all of these reactions already. We've already talked about alcohols a lot in this class. We're now focusing on them in this particular chapter. We have talked about alcohols, and we've talked about many ways to make alcohols. So we saw in chapter 7 that substitution reactions can yield an alcohol if we, depending on the conditions, if we have a good leaving group like a halogen, we can replace that with an alcohol. In an SN2 type reaction, that would be by using a sodium hydroxide, an OH negative. It's a very good nucleophile. If we are going through an SN1, we can use acid catalyzed hydration. We can use water. If it's primary, we need to go through an SN2, so then we'll use a strong base like sodium hydroxide. That's also a very strong nucleophile. Tertiary must go through SN1, so we can use our H2O, and you can catalyze this reaction a little bit with acid if you need to. But this is just our H2O reaction. So that would force it, because that's a weaker nucleophile. You don't really need acid for this one, because chlorine's already a good leaving group. So that's our SN1. Secondary, we can go through both. We can't really use a stronger nucleophile for the SN1 because that's going to make the reaction more slow. We have to form that carbocation, if we have a strong nucleophile getting in the way. Plus, remember, if we have a very strong nucleophile, it's also a good base, and we're going to get the elimination product instead of the substitution product. It's always something to remember that elimination is always competing with substitution. You should always be remembering that concept. So this is another case where if we use sodium hydroxide, we'd likely just get the E1 elimination or the E2 elimination and not the substitution product. And if we do the elimination, we're going to end up with a product with a double bond, not a product with an alcohol. So we're trying to make alcohols. In chapter 9, we learned that if we start with a double bond, we can make alcohols, and depending on our regioselectivity and our stereoselectivity, we can use different reagents. Again, none of this is new, you just took a test on it. So dilute H2SO4 is great for acid catalyzed hydration. If you have a very symmetric compound, you don't have to worry about carbocation rearrangements. But anytime a carbocation rearrangement is possible, that will lead to majors, so that gives you problems. So typically your acid catalyzed hydration is not going to be your most useful reaction unless you have a compound where a rearrangement wouldn't matter. You're going to get the same structure. Remember, you're going to get both stereocenters. So if we want the most substituted alcohol, and then we can use our oxymercuration, demercuration. that is going to also put our alcohol in the most substituted position, but the mercury prevents any carbocation rearrangements from forming because we don't have a full carbocation. We have that carbocation being stabilized by a resin structure with the mercury with the positive charge. So that's really important. Now, we've been talking about hydrides. This is sodium borohydride. That's another source of H negative. We're going to be seeing that more in this particular chapter. Hydrogen is more electronegative than boron. Boron is on the other side of carbon on the periodic table. And remember, hydrogen has almost the same electronegativity as carbon. So, then our H is negative, and it replaces our mercury, basically by acting as a nucleophile and pushing it out. And here we need H2O for this to put alcohol. If this was an OR group, this would be an OR. So we have to react with H2O to get the alcohol. And then our last one that we talked about is our anti-Markovnikov hydration, and that's using BH3 and THF followed by peroxide and sodium hydroxide. And that puts our alcohol in our least substituted position. Remember, that's going to be syn addition if we form two stereoisomers. So we know ways to form alcohols already. We've done these. So the answer is all of these can form alcohols. And they're all reactions that we have talked about in a lot of detail in the last couple of chapters. This class, you can never forget anything you learned. If you had trouble in test 1, you're going to have trouble in all the tests in this class. Because this class builds upon itself, and we use all reagents and all reactions that we've ever done in every chapter in this class. This class highly builds on itself. That's one of the things that makes this class hard. You can't just forget what you learned from a test and go on to the next one. You have to have understood that material. Once you get behind in a class like this, you get behind, and you really have to work harder to get back. So that's always something to keep in mind, that this class, more than any other ever heard of or took or taught, builds on itself. We're going to be putting together more synthesis. You're going to use reactions from every section we've talked about. And again, it builds on itself. We repeat a lot. Again, we're repeating these things we've already learned. But this class absolutely builds on itself. So if you are having problems, as soon as I get the test graded, you should have them by Monday. You need to go through that. Don't put it on the side and figure out what you did wrong, or you're not going to pass this class. Because it does build on itself. You really have to understand the basics. If you're trying to memorize, you're going to overwhelm yourself. It's just not possible. Well, it might be possible for the few people that have, photographic memories. But if you don't have a photographic memory, it's going to be really hard to memorize things. You have to understand everything we've talked about. So as you can see, it's already starting to, you need to remember everything we've talked about. The next thing we're going to talk about, I've mentioned reduction and oxidation. And you learned about reduction and oxidation in general chemistry. And you learned all those rules, which I hate. I hate those rules. Now I'm going to teach you how you can do reduction and oxidation without knowing those rules, what it's based off of. So, and this is going to be important because we're going to talk about how to go from an alcohol to stelvano and things like that, and what we mean by when we say something is reduced or oxidized. Typically in organic chemistry, there's a difference in oxygens, which is why we use oxidation reduction, but that's not necessary. Remember, it's just a difference in electrons. So let's talk a little bit about reduction and oxidation. It involves a change in oxidation state, which is just a way that we follow electrons. So when we're talking about formal charge, what we're thinking about when we're calculating it is if we had this molecule and all of the covalent bonds broke homolytically, which means one electron from each bond goes on one atom and the other electron from each bond goes on the other, then we can calculate formal charge. If the amount of electrons after we do that is equal to the amount of electrons that it should have, it has a zero formal charge. That's where that calculation comes from. So if we look at our carbon here, our carbon is neutral. It has a partial positive charge, but it's neutral by formal charge. Because if each of these four bonds break homolytically, carbon has 4 electrons and the hydrogens and the oxygen each have 1. carbon should have 4 electrons based on where it is in the periodic table. So we have a formal charge of 0. That's formal charge. However, reduction oxidation, you're treating bonds as if they're breaking heterolytically, where the electrons are going to go, both of them from the bond, to the atom that's more electronegative. Like this. So, when we're calculating oxidation state of carbon, we are going to think about what if all of the bonds that carbon is participating in broke heterolytically, and carbon took the electrons when it's bonded to something more electropositive, but if something is more electronegative, that takes the electrons. So here we're comparing carbon and hydrogen. Hydrogen is slightly less electronegative than carbon, so carbon gets those electrons. We have 3 hydrogen bonds, but our bond between carbon and oxygen's more electronegative than carbon, so the 2 electrons go to the oxygen. So the oxidation state is based on the fact that carbon should have 4 electrons, but it has 6 electrons if we think about the bond breaking heterolytically, where the electrons go to the atom that's more electronegative. That's really where those rules come from that you learn in general chemistry. If you look back at the rules, if you open your Gen Chem book and look at the rules, what you'll see is the electrons are going to the more electronegative atom. When you look at the rules and it's like, okay, here's the non-metals, and then it lists them in order, it's in the order of electronegativity. And so you can look back at those rules, and that's the basis of oxidation state. So you don't have to memorize those rules if you understand this. So the oxidation state here is, it has 6 electrons, 1, 2, 3, 4, 5, 6. It should only have 4, so that's 2 more electrons than it should have, so the oxidation state is -2. Fairly straightforward. You don't have to memorize those rules if you can do this. And of course, that's carbon's oxidation state. And in most cases in organic chemistry, when we're describing oxidation reduction, we're talking about what's happening at the carbon. Because of course, if carbon is being oxidized, something else is being reduced. But we're usually describing, when we're saying this is an oxidation reaction, we're describing what's happening at the carbon. So you can calculate the oxidation state of all atoms, but we don't really care, we care about the carbon. So let's look at these. So our methane, what's our methane's oxidation state? Again, here we know carbon-hydrogen is nonpolar, but we're actually going to do this based on electronegativity, and carbon is slightly more electronegative than hydrogen. So that means that all 4 of those bonds are going to break, and all of the electrons are going to go on carbon. So that's how many electrons? There's how many electrons in those bonds? And how many bonds? So how many electrons? 8. So the carbon has 8 electrons. How many should it have? Should have 4. So what's its oxidation state? -4. Our oxidation state from carbon can range from -4 here to +4. So let's look at methanol. We just calculated that. All of the carbon-hydrogen bonds are going to go on carbon, but oxygen, stop that, is going to take the bond. So that should have 4, but what we have is 6, so that's an oxidation state of -2. Now in formaldehyde, we have carbon-hydrogen, so those electrons are going to be on carbon. Stop that, why are you doing that? But what about the bond between carbon and oxygen? How many electrons do we have in that bond? How many bonds do we have between carbon and oxygen? So how many electrons? 4. All those electrons are going to go on which atom? Oxygen. So that means carbon has 4 electrons. How many should it have? 4, so its oxidation state is 0. And formic acid, what oxidation state do we have? +2. And then in carbon dioxide, our most oxidized carbon, positive 4. So our oxidation state can go from least oxidized, -4, to more oxidized, +4. Now again, oxidation really comes from the fact that when it was first observed, notice we have more oxygen bonds to carbon. And in organic chemistry, that's often true, not always. Because we also have oxidation reduction occurring when we go from a pi bond between two carbons to a single bond. That's a reduction. So there's no oxygens there, but it's still considered oxidation or reduction. But in a lot of cases, we do have a difference in oxygen, and a lot of oxidizing agents, which are reagents that cause oxidation to happen, contain a lot of oxygens. So you'll see that throughout organic chemistry. So oxidation is an increase in oxidation state. -4 to -2, that's an increase in oxidation state. -2 to 0, that's an increase in oxidation state, and so on. And our most oxidized carbon is going to be carbon dioxide. Reduction is a decrease in oxidation state. So the conversion from formic acid to carbon dioxide is an oxidation. And the conversion from formaldehyde to methanol is a reduction. When we are talking about the carbon, and we're usually talking about the carbon, remember, if something is causing the carbon to go through oxidation, something else is being reduced. That's usually our reagent. So our oxidizing agent, a reagent that we add in to cause oxidation, that's going to be reduced. It's causing the carbon to be oxidized. Like I said, most times we do see an increase in bonds to oxygen with carbon. But remember, what we're really looking at is the difference in electronegativity. So technically, if we have a formaldehyde and then we form an acid chloride instead of a carboxylic acid, that's a change in oxidation state because chlorine is more electronegative than carbon. But oftentimes what we're describing is an increase in oxygen bonds. And we've done oxidations. Some oxidations we've done, ozonolysis. Ozonolysis is an oxidation. Our acid catalyzed hydrations, all of those are technically oxidations. And of course, our dihydroxylations or oxidations, especially when we're talking about KMNO4, that's common oxidizing agents. So if you know what this is, what oxidation, reduction, how to calculate these like this, you don't have to know those rules. I hate teaching those rules in general chemistry. I hate teaching anything that you have to memorize. I like teaching this is why it happens. And it's based on electronegativity. So you should be able to do this, and on a test or quiz, you should be able to assign oxidation state of a carbon and tell me if something's being oxidized or reduced. Or not. It might not be changing oxidation state at all. For example, we're going to spend a lot of time in what we call carboxylic acid derivatives. This is our carboxylic acid. We can react that to form an acid chloride. This is not an oxidation or reduction because our oxidation state is +2 in both cases of this carbon. So this is neither. It is a reaction, but it's not an oxidation or reduction reaction. And that's why we have a whole chapter on carboxylic acid derivatives. It's molecules that have the same oxidation state as carboxylic acid. So we have that all in one chapter, which we'll do for the last test. We won't get to that just yet. Why are we talking about that? Because if we have a carbon-oxygen double bond, we can reduce it to an alcohol. If we have an alcohol, we can oxidize it to a carbon-oxygen double bond. And that's really useful in synthesis. So we're going to be talking about that process. So you have to understand oxidation and reduction. So if I was trying to take carbon-oxygen double bond, and again, our oxidation state for that is 0, and we're trying to get to an alcohol, that is a reduction. We're going from the oxidation state of 0 to oxidation state of -2. Again, all of these carbons are neutral. So this isn't formal charge, this is oxidation state. What kind of reagent do we need to do this? And the answer is, let's look at the difference. So the carbon, our alpha carbon, CR1, that carbon of our carbon-oxygen double bond, has 0 hydrogens on it. And then in this example, my carbon has one hydrogen on it. So what kind of reagent do we need to add a hydrogen to a partial positive carbon? And we're going to need a reducing agent that has a hydride, an H negative. In other words, a hydrogen nucleophile. If we have a hydrogen nucleophile, it can attack our most partial positive place, here, our most partial positive carbon. And remember, a carbon-oxygen double bond has a resonance structure. I don't know why this thing is doing this. It's not supposed to be changing when I write on it. So there's our resonance structure. So that means that a nucleophile can attack that position pretty well. So if we want a new hydrogen bond, we can use a hydrogen nucleophile. For a hydrogen nucleophile, we need a hydride. For a hydride to form, what does the hydrogen need to be bonded to? A metal or something more electropositive. In most cases, it's a metal, but boron is also more electropositive than hydrogen. So we need a source of hydride. This can't be an acid. An acid has a partial positive hydrogen. That hydrogen is not going to be a nucleophile. That hydrogen has no electrons available. We need a hydrogen that's bonded to something more electropositive than it, so we can have a negative charge on the hydrogen. So we can have a hydride, an H negative. That H negative will have a lone pair or a partial negative charge, depending on how strong our hydride agent is. So HCl is not appropriate. HCl is not a hydride. HCl is an acid. Hydrogen is more electronegative. A more electropositive. I don't know what is going on with this thing. It's not even doing blue. Maybe the computer needs to be restarted. I don't know. Nope. Okay. So what we have is an HCl, and there we have a negative charge on hydrogen. Because our hydrogen is more partial positive, so we can never have an H negative. This has no electrons. It's not a source of hydride. So what we need is a source of hydride. So our common reducing agents, we're going to talk about them. And we're going to talk about their selectivity. So I just showed you 3 reducing reagents. Source of hydrogen. First is one we've seen before. We've reduced pi bonds, and we're still reducing a pi bond with it. H2, platinum, palladium, or nickel. They can work for our carbon-carbon pi bonds. They can also work for our carbon-oxygen pi bonds. The problem is they're going to reduce anything. They will reduce double bonds, triple bonds, and carbon-oxygen double bonds, and we can't stop them. And the reason why is because the catalyst catalyzes all pi bonds. So we don't have any selectivity if we're using this reagent. It's useful if we want to reduce all pi bonds in the structure. It's useful if we don't have any other pi bonds but our carbon-oxygen double bond, but it's not useful if we want to selectively only reduce our pi bond. So again, reactivity, and in this case it's more reactive because of the catalyst, reduces our selectivity, just like we talked about before. We're typically doing high pressure, a bit forceful conditions, so we can reduce everything. So if we don't want to reduce carbon-carbon double bonds, we can use a source of other type of reducing agent, and that's a source of hydride. So reagents that donate a hydride are generally pretty good reducing agents, but remember, a carbon-carbon double bond doesn't have a partial positive and partial negative charge, so they don't react with carbon-carbon double bonds. We have no polarity in our carbon-carbon double bond, but we have polarity in our carbon-oxygen double bond. We have no resonance structure here, but we have a resonance structure where we have a full positive charge on the carbon and a full negative charge on the oxygen. So hydride reagents won't react with this because there's no negative partial positive charge within the reactor. So our 2 hydride reagents that we're going to talk about, and we're going to talk about the selectivity, is sodium borohydride, which we've seen to remove our mercury and oxymercuration, demercuration. So again, we have a boron that is attached to hydrogen. Boron is more electronegative than hydrogen, so hydrogen has that partial negative charge. This is going to be our weaker reducing agent because boron isn't that electropositive, but it is more electropositive. So we're going to see that we can reduce ketones and aldehydes with it, but that's it. We can't really reduce anything else. And our solvent is going to be our source of H+. So once our hydride reacts, and I'm showing it with the covalent bond between boron and hydrogen, so the electrons are coming from hydrogen. You can also, and I will accept, you drawing the hydride as your nucleophile, because this is a source of hydride, so you can draw it either way. Remember, the sodium is just your counter ion. Once it attacks, that leaves a negative charge on oxygen, which can then be protonated with water. Now, we can't use a strong acid in this reaction because H negative is not only a strong nucleophile, but it's also a strong base. So we don't want to use any strong acids in this reaction, which means we're never going to form positive charge. Notice we're only forming negative charge. The other reducing agent we're going to talk about is lithium aluminum hydride. Now, this is a much stronger source of H negative because here our hydrogen's bound to a metal, aluminum. So aluminum is much more electropositive. You'll sometimes see this as LAH, lithium aluminum hydride, or LiAlH4, which is the actual ionic molecule that forms. And it's the same mechanism, and I don't know why I have this with boron, but it's the same mechanism. The H negative attacks, and the proton source is added. The main difference here between this reaction and the other one, notice I don't have a 1 and a 2. Sodium borohydride is mild enough to react in the presence of water. Lithium aluminum hydride will catch on fire in the presence of water. So you cannot add water until your hydride has been reacting. And then you slowly add water as a proton source. Again, hydride is negative. It's a strong base as well as a strong nucleophile, so we cannot form any positive charges. It's also going to be more reactive, so we're going to talk about reactivity of lithium aluminum hydride and how it differs from sodium borohydride. You need to know the difference in selectivity for these things. All right, you guys have a good weekend. I don't know what's going on with my system. I'm sorry, I'm having technical issues. Most of what we did today was a review on acidity. You were confused about that, make sure you go ahead and reread chapter 3.